To calculate the biodiversity of a habitat, counting the number of organisms present often does not tell the full story. For example, a habitat could have 100 animals, but 99 of them could be cows, and one of them could be a sheep. Alternatively, there could be 100 different species within a habitat. There could only be one of every single species. A holistic understanding of biodiversity should account for both factors: species richness in the first example and species evenness in the second example. This is where Simpson's index of biodiversity comes in. It considers both species richness and species evenness, and here is the formula for it. D represents Simpson's index. Lowercase n represents the number of organisms in one species. And capital N refers to the number of organisms in all the species. The sigma sign here just means the sum of, so you're going to be doing this calculation for every single one of the species. But let's break this down. So, a D value, or a Simpson's index value of 1, represents infinite diversity. This means that the habitat has lots and lots of animals from lots and lots of different species. A value of 0 means no diversity. This could mean that there is a huge imbalance in the number of species, so in that first example, like 99 cows and 1 sheep, or that there just aren't that many species present in the habitat. The division between lowercase and uppercase n here ensures that species evenness is calculated, because it's a ratio between each species' organisms and the total number of organisms. The sum of all the species, represented by the sigma symbol, ensures that all the species are accounted for and calculated. The 1 minus here just kind of makes results easier to analyze, because it's a lot easier to understand 0 as no diversity and 1 is infinite diversity, as opposed to the other way around. Let's now work through an example of a question that could come up using Simpson's index of biodiversity and calculating it. So here we have a pond species with 5 different species. We're given Simpson's index of diversity, the formula down below. We're given a bit of information about the sampling techniques that aren't particularly necessary, but we're asked to calculate D, essentially. So what's the first step that we want to do here? So D is obviously what we're trying to calculate. There are 3 variables. We're trying to work out this, and these are given to us in the table. So each of the small n values is going to be 4, 6, 3, 8, and 2 respectively. And what we need to work out is capital N, the total number of species. So doing this is a pretty easy mathematical sum. You just do 4 plus 6 plus 3 plus 8 plus 2. The number of species in each habitat, the total number is just going to be the total number of organisms, elementary, is equal to 23. Now, here comes the more complex part. Next, for each one of these species, for the water boatman, the water strider, the dragonfly larvae, the mayfly larvae, and the caddisfly larvae, you are going to do the lowercase n over capital N squared. So for the water boatman, you do 4 over 23 all squared. For the water strider, you do 6 over 23 all squared. For the dragonfly larvae, you do 3 over 23 all squared. For the mayfly larvae, you would do 8 over 23 all squared. And for the caddisfly larvae, again, you would do 2 over 23 all squared. Once you're given these values, which should come out to 2 significant figures, about 0.03, 0.07, 0.02, 0.12, and 0.01, then this is where the sigma sign comes in, because you are going to add all of these values together. You're going to do 0.03 plus 0.07 plus 0.02 plus 0.12 plus 0.01. and this would give you 0.25. But this is not your final answer. This is just the initial value that you're going to need to plug back into this equation, because 0.25 is this. It's the sum of all the ratios. Next, to work out the Simpson's value, you're going to need to do 1 minus that value to get 0.25, which would mean that your final answer will be 0.75. Now, this question doesn't ask you to write any kind of concluding statement or analyze the data, but if you did, you would just have to write a concluding statement saying that a D value of 0.75 means that there is a high species biodiversity. Because as we mentioned before, value of 1 means infinite diversity, value of 0 means no diversity. So since 0.75 lies considerably closer to 1 than to 0, there is a relatively high species biodiversity in the species. And that's all you need to know about Simpson's index of biodiversity.